Laplace transforms. We've been working with Laplace transforms, and we're finding transforms of a bunch of functions, piecewise functions we started with, and then we'll see with those piecewise functions we might be able to find a shortcut based on a general piecewise function. And then a little bit later on we'll talk about the Dirac delta function. And that delta function is a special function where it's infinity at one point and 0 everywhere else. So it's a piecewise function where it's 0 except at that one instant where it's infinity. It's kind of like a weird, mathematically, it's described as a limit because it's like a weird scenario, but it's an actual. It could represent a real life problem. So imagine that spring problem that's going back and forth, and then you take a look at the what do you call it? The mass in the spring, and then you hit it. That hitting that spring is like an instant of displacement, and then after that you just let it go. Then it just goes as it goes. So I think that's that's an important function to be able to deal with in engineering and stuff. So the Laplace transforms will help us deal with that kind of a function. But we're using Laplace transforms to solve differential equations, which means we need some information about derivatives. So if our example, for example, if we have, well, let's just make a single derivative. We want to be able to transport any sort of differential equation into the Laplace world. And so a lot of that will have derivatives involved. And so we need to find the Laplace transform of a derivative. And so we generally would look at it like L of some derivative. Well, let's first say that L of y without the derivative would be some y function. Y is a function of t in the real world, and now we're going to have y as a function of s in the Laplace world. Remember how I write my y's kind of all weird like this? This is capital Y. So in the Laplace world, I'll have y of s, whereas in the real world, I'll have y of t. So the question is, what is L of y prime of t? So if we go back to the, let me see, I don't know if I want to do this. I just tell you, but maybe I should try to see if I can think about deriving it using the definition, which is what we should be doing. So this is going to be a what do you call it? An improper integral of e to the minus st times y prime of t dt. Now, what I'd like to do is I'd like to see if I can write this as some function of y without the derivative. And so it looks like it might be appropriate, you know, if I have a derivative of something multiplied by something else, maybe I could do by parts, yeah. So if we do integration by parts, we're going to let u equal to, this is the one I'm going to need to take the derivative of, and then du or dv equals y prime of t dt. This will bring me to the original y of t, and then du is going to be, so this is a derivative you multiply by also we're integrating with respect to t, so s is a constant, so it's going to be minus s e to the st dt. Need more space. Let's see if I can. Wow. All right. So that's the transformation, or that's the substitution for by parts, and then I'll have an e to the minus st y of t from 0 to infinity, and minus the integral of v du. Well, this is my b, sorry. Minus s e to the minus st times y of t dt. All right. Is that right? Did I do that right? I hope so. Otherwise, we're going to get the wrong formula. So we have e to the st in the denominator, and as st as t goes to infinity, y to the t, it doesn't matter what that's going to be because it's going to go to 0. So it's just a matter of putting 0 in here. So it's going to be at infinity. I'm kind of fudging the correct way to do improper integrals here, because that's just for kids. that's for calc 2. There's theory behind that, and I'm just going to fudge that. So at infinity, it's going to be 0 minus, and then at 0, this is going to be e to the 0, which is 1, y to the 0. I'll fix that up in a few minutes. So that's that part. And here, why don't I just take out the negative s, and then I'll have the integral from 0 to infinity of e to the minus st times y of t dt. So what's the value of this? What's the value of e to the negative st y of t? Remember, in the beginning I said we wanted things in terms of y of t instead of y prime of t. So what did this buy us? This is the Laplace transform of y, right? Which we said was just capital Y of s, and we're going to change this to capital Y of s. We have an s over here. That's because Laplace transform is a linear transformation. We can move constants out. I mean, we kind of moved it out of the integral. So, and then here we have negative. Is that a minus? That's a minus y of 0. Okay. So that's it. It turns out that our Laplace transform of the first derivative is going to be s times y of s minus y of 0. What's y of 0? Well, that's the initial condition that we're going to use. Okay? Yeah. So, where was the cheating part? Yeah. Yeah, so there's restrictions here, and there's restrictions here to make sure that as long as y is not some sort of exponential function that would make, this thing all go off to infinity. So that's the only hand waving that I'll do. Well, y could possibly be an exponential, but it has to be an exponential function that would work well with e to the negative st. So there are restrictions to in doing this, and we'll just assume that the restrictions will take care of themselves. Or you can look through the theoretical part in the book and get the information from there. So this is our formula for the first derivative. Is this easy? Is this is a first order linear, right? So we can like integrating factor and figure this out. Because maybe this could be our first example. Ooh. All right. So let's continue on with this example since we're here. We know that the I guess we should use t's. Sorry. What's the L of what's the transform of t? You remember? It's like some n factorial divided by x to the n plus 1. So t is equal to 1. So what should it be? 1 over s squared. Okay. And let's throw in an initial condition. Let's say y of 0 is equal to, let's pick a number. That's fine. That's not too big. Oh well. All right. So let's say we're doing this problem where we're trying to solve for y prime plus y is equal to t, where y of 0 is equal to 9. Okay. So let's take our example down here. All right. So according to our so the plan is to go into the Laplace world, right? So we're going to be in the Laplace world, and we're going to replace the y prime with s capital Y of s minus y of 0 plus y, which is just y of s, is equal to, and then the t into the Laplace world is going to be, what is it, 1 over s or s squared? S squared. Okay? So in the Laplace world, remember, all you have to do is algebra. You don't do any calculus here. And if you replace the y of 0 with 9, then you just have an equation where you're trying to solve for y of s. Before we do that, let's just make sure that we're understanding that this is the L of y prime, and this is the L of y, and this is the L of t. All right. In the Laplace world, we have s, y of s, minus 9 plus y of s is equal to 1 over s squared. Shake off your algebra brains here. We got s minus 9 y of s is equal to 1 over s squared. And so y of s is 1 over s squared s minus 9. Easy. Oh, did I do that wrong? What happened? Minus 9. Oh, yeah. Guess it wasn't that easy. I was just getting too excited here. All right, let's try that again. We got s plus 1 y of s minus 9 equals 1 over s squared. So I suppose we need to bring the 9 over. I guess we should have brought the 9 over first. S plus 1 y of s equals 1 over s squared plus 9. And I think I would leave it like that, and instead of trying to combine into common denominators, because when you're solving for this, what you're going to want is you're going to want different terms, and this is where partial fractions is going to come in. And so if I were to combine this into one fraction, then I'll have to split that up again. So try to get it split up. And if you don't get it to split up, then you'll have to eventually split it up. So 1 over s squared, s plus 1, plus 9 over s plus 1. Now, did I do it right? I hope so. So the idea is to bring this back to the real world. So what we want to do somehow is to get this back into the real world. What we're going to need is we're going to need our formulas, our table of values. Maybe we should get into the habit of writing our table on the side of the board over there so that we can remember. I think I vaguely remember there's a 1 over s plus something, s minus a. So that would be e to the at. So 9 times 1 over s minus negative 1. So 1 over s minus a is something that should be familiar to us. But this one, I don't recall seeing anything with an s squared or s cubed plus s squared or anything like that, right? So before we can take this back to the, well, let me write down a few of the formulas that we should probably know. We know that t to the n goes to n factorial over s n plus 1, right? We know that e to the at is going to go to 1 over s minus a. We have some sines and cosines also. I think we can not worry about the sines and cosines. But based on these two, I have like an s squared and a s plus 1 possibility of combining things. So it looks like what I need to do is I need to, before I jump back to the real world, I'm still in Laplace world solving for this. I think what we need to do is we need to split this up using partial fractions. Or actually, partial fractions would technically have an s and an s squared and s plus 1. Okay. So I was a little too eager to go back. Before we can go back, we need some more algebra. So we have 1 over s squared s plus 1 is equal to a over s plus b over s squared plus c over s plus 1. So if I multiply everything by the common denominator, I would have 1 is equal to, and then a common denominator here will be an s plus 1, b, s plus 1, plus c, s squared. Plus ax plus b, you would have a linear term if you have an irreducible quadratic in the denominator. And having an s squared is not an irreducible quadratic. It's a linear that's multiplicity 2. So let's continue on over here. We're going to get 1 is equal to a s squared plus as plus b s plus 1 plus c s squared. Is that right? Maybe I should multiply the b out. This is just bs plus b. So this is going to be 1 a plus b, or a plus c, s squared. And then I have a plus b, s. You could do that. Yeah, do you guys know like little shortcuts for doing this? Yeah. Like right here at this point, instead of multiplying it out like I did, you can just let s equal to some choice numbers like 0 or 1. Yeah. Yeah, well that's where I'm getting at, but even before that, there's a little bit of a shortcut. It gets freaky when you have multiplicity, which is why I'm not using it here. But it's still doable. All right, let's do this. Let's continue on. So just by rearranging this here, we can imagine that we have a 0s and a 0s squared. So we know that a plus c is equal to 0, a plus b is equal to 0, and b is equal to 1. So b is equal to 1, a plus b is equal to 0, and a plus c is equal to 1, or 0. So if b is equal to 1, then a is equal to -1. If a is equal to -1, then c is equal to +1. So here are our values. So then we can put a -1, b 1, and c 1. And then if we include this other one here, we have a 9. Hey, we can combine this to 10, right? Okay. So this is refreshing memories. The door. Wow. Oh, look, read my writing. Okay. Partial fraction stuff. All right. So some of the key things that you want to try to remember about partial fractions. Um, the simple cases are, we have an x minus 1, x plus 1. So those are two linear terms. The order doesn't matter as long as you're consistent with whatever you have on the right-hand side. So that's the simplest case. If we have 1 over s squared, s plus 1, which is what we have, this is technically a linear term, s minus 0, with multiplicity of more than 1. And so whenever we have something with multiplicity more than 1, it's going to repeat up to that power. Actually, let's make this one multiplicity 3, and we'll see how that plays into it. So this is going to be, for the s's, I'll need an s and an s squared. And for the s plus 1, I'll need an s plus 1 squared, and s plus 1 cubed. Okay, so it has to repeat. Now, these are all linear. So the numbers that are on top are all constants. A, B, C, D, all constants. Okay? So let's try to throw you off a little bit. One of them is an irreducible quadratic. The other one can still be factored into linear terms. So before you break this up, what you want to do is you want to factor as much as you can until you can't factor anymore. So the first term, the first factor here, s squared plus 1, is an irreducible quadratic. And then this one can actually be factored, so you have to treat it like two linear terms. It's not an irreducible quadratic. Yeah. Plus 0x if you want to put that middle term. Yeah. So if you have an irreducible quadratic, nothing else you can do. You're just going to have to keep it at that, which means when you break up your partial fractions, on top of the irreducible quadratic, you have to have a linear term. Meanwhile, these other ones are linear, and so you can put constant terms on top. So you need a linear term on top of an irreducible quadratic, and then you just have constants for all the other linear terms. Are there any other things that you vaguely remember from partial fractions that we might need? No, they do exist. Do they exist? No, they don't exist. Because you're guaranteed at least one. Yeah, you're guaranteed at least one root. Mm. Yeah, so that's the part where you're trying to solve for A, B, C. Mm-hmm. Yeah. All right, so we'll come back to this page, partial fraction stuff, if we run into any more. So meanwhile, let's go back to what we were doing here. We got this partial fraction set up, and we found A, B, and C, and now we have our right-hand side. Actually, let me rewrite that over here. So still in the Laplace world, we have a y of s is equal to -1 over s plus 1 over s squared, and then I'll combine the two here, plus 10 over s plus 1. So now let's see if we can bring it back to the real world. So doing the inverse Laplace of capital Y is going to be little y of t, which is our solution. And now we have to remember what 1 over s was. You remember what 1 over s was? Was it just constant, right? So -1 plus 1 over s squared, that was the t, plus, now we have a 10, e to the negative, remember this is s minus -1, so e to the negative t. Now we got our solution. I hope it's right. So let's brush up on our integrating factors, which you'll need to know for the final exam. I mean, that's the most basic, aside from the separable differential equations, which you can do in Calc 2. Integrating factors is like the first real process that we're doing in differential equations, and you got to know how to do that. So this is our differential equation, y prime plus y equals t. And so let's find the solution for this using integrating factors. You remember how that goes? So our integrating factor is going to be e to some integral of the term here, right? Just t, or just 1 dt. Was it negative or positive? It should be negative. So the 1 here is the p of t that we want to throw into this integral, right? So 1 dt, and that's just going to be e to the negative t. So we integrate everything by e to the negative t, y prime, it's positive. Is that why? So the whole idea behind an integrating factor is to treat it like it was a product rule. So this is y times e to the t is equal to, or d dt of that. So we integrate, you get y times e to the t, and then we integrate the right-hand side. Sorry, this is just a t. And then this is going to be the what do you call it? Thing. Parts, integration by parts. So u dv, so u is going to be equal to t, and then dv is going to be equal to e to the t. So uv, that's t e to the t, minus v du. Du is equal to 1, and v is going to be e to the t. Is that right? Plus our constant. And then you solve for y. This is going to be t minus 1 plus e to the c times e divided by e to the t. And then we put in our initial condition, y of 0 is equal to 9. You put 0 in there, we're going to get 9 is equal to 0 minus 1 plus c, so c is equal to 10. So our solution matches. I'm glad that it does. and and now we can use Laplace transform. I mean, we just verified. Let's just check. We're going to check using, in this particular example, we're able to check using integrating factors. Okay. It matches, right? We got 1, the -1, the t, and then a 10 e to the, yep. Cool. That's nice. All right. So, yep, that's what we did. Done. We done did it. And now we have to just uh, be able to do stuff like second order and third order and stuff like that, which means we need some more information about higher order derivatives. And it turns out there's a decent formula for Laplace transforms of higher order derivatives, and here it goes. Yeah, that's before. Yeah, the main thing that this is used for, like weird functions like piecewise functions and that delta function that I was talking about. Um, and then anything else that might not work with whatever else. Come up with what? This I didn't come up with that. Well, they just did what we did, um, and they just put double prime in here, do integration by parts a couple times. Oh, Laplace transforms. Yeah. He was just, these like mathematicians in the old days, they didn't have to worry about social media or politics. Oh, some of them worried about politics, but they just sat around thinking. And so they just thought, well, yeah. I mean, if you were really that interested, you would sit and think about these things. And if you're a genius, you'd figure it out in a couple of hours. And if you're not, then you figure it out in a couple of years. But you kept on thinking about it. Or maybe you wouldn't have figured it out and you just died wasting your time. But yeah, more people than not didn't figure it out, and they died, and they didn't have any theorems named after them. But that's okay. I'm sure what they did contributed to somebody like Laplace. So Laplace probably took some information from somebody else who thought about stuff and didn't get very far, and took that and carried it on and found Laplace transforms. I don't know. I'm just making shit now. It's all made up. Yeah. Oh no, because there's convolution theorems. that allows you to do stuff. But we're not. I don't think we're going to talk about convolutions. Yeah, it gets convoluted. Well, the idea is that it's supposed to be easier. Uh, that's the idea. The piecewise functions, when we get to the piecewise functions, you'll see that it would be good to use Laplace transforms. So the idea is that it'll make it easier for some other stranger functions that we're going to be dealing with, piecewise functions and the delta function. Otherwise, some of the other techniques that we learned are like easier shortcut ways of finding, like, the auxiliary equation. Is that what it's called here? It's not the indicial equation or anything weird like that. I'm mixing up classes now. Yeah, so the auxiliary equation will help us find our solution quicker for first order or second order linear with constant coefficients, right? And so that might be easier than Laplace transforms. But we can't use that if we're going to have more complicated things. So now that we have this, let's see, are we brave enough to do a third order? Oh, let's just do a second order. So let's do a second order differential equation. Any 35 through 38 here? Anybody want to pick one out? 37. I don't have one. Oh, there's one in the homework? Yeah, that's for your homework. If we have time, we'll do one. No. Okay. The hard part is partial fractions. Okay. So third order just means we probably have a third order partial fractions and stuff. Yeah, no, I meant like a third order fraction that we might have to decompose. I mean, it might all decompose to linear terms, which would be great. Yeah. But the cubic is always going to be reducible, at least by one real number and possibly two complex numbers or three real numbers. Yeah. Yeah. Cubic would always hit the x-axis somewhere. Good. You got your algebra down. All right. We're doing this and we're implementing our newly found differential equation, or Laplace transform of any order differential equation. So the highest order here is 2. So let's just write out the formula for the transform of y double prime. So n is equal to 2. So the largest s that we have here is s squared. And we'll change it to y of s. And we're going to keep going down with a power. So s squared minus s to the first power. On this one, we don't have the original y now. We have the little y of 0. And then minus one less derivative, and then y prime of 0. Do you guys see how that happened? So when n is equal to 2, the highest power here is s squared. And then the highest power, s, is going to be attached to the unknown function y that we're solving for. And then what comes after that are s with less derivatives times the little f evaluated at 0. So that's our y evaluated at 0. And then our next term, which is going to end up to be our last term, is going to be this. So n is equal to 2 These are the terms that we have. Oh, this just says if n is equal to 15 or something, then there's like a whole bunch of them that you need to keep going down to. And then you have 15 minus 1, that's 14. So if this is a 15th order differential equation, your initial conditions have to cover up to 14 derivatives. So here we have a second order differential equation. We need to cover the first order derivative. Yeah. All right. Let's get this started. Yes. Yes. All right, let's do the Laplace transform of this, and we found the Laplace transform of the second derivative. So that's s squared y of s minus s times y of little y of 0 minus y little y prime of 0. So that's your y double prime. Your y is just the y. Square root of 2 is a constant. Let's just throw that square root of 2 out. And then now we need the Laplace transform of sine. Remember the sine is the one with a constant up on top? Sine and cosine, yeah, cosine has the s on top. And they both have an s squared plus k squared in the denominator. That's your irreducible quadratic that we're going to be dealing with. So a constant is square root of 2. All right, so we've taken the transforms of these things. This is your y double prime, this is your y, and this is your square root of s times sine square root of, or square root of 2, sine square root of 2t. So now we're in the Laplace world doing algebra. Let's do some algebra. We got s squared y of s minus, now y of 0 is 10, so I'll put 10s here, and y prime of 0 is 0. And then on the other side, we have square root of 2 times square root of 2. We'll call that 2 for now, and I'm sure we're going to come back with square root of 2 later on as our solution. All right, so we're still solving. We got our I on the y of s that we're solving for. Everything else is a constant that can go on the other side. So I have an s squared plus 1 y of s, and then 2 over s squared plus 2, and we'll bring the 10s on the other side. We got y s is equal to 2 divided by s squared plus 2, s squared plus 1, plus 10s over s squared plus 1. Now, the second one looks nice. It looks like it's a cosine function, right? The 10 is a constant, so you have s divided by s squared plus 1, so that's great. The other one looks like it has some issues. So this will be the last partial fractions I'm going to do by hand. Everything else I'm going to put into Mathematica from now on. So we have a 2 divided by s squared plus 2, s squared plus 1 is equal to, those are two irreducible quadratics. as plus b over s squared plus 2 plus cs plus d over s squared plus 1. All right, so get rid of the denominators. I have as plus b is going to get multiplied by s squared plus 1 plus c s plus d gets multiplied by s squared plus 2. Looks like I'm going to do some multiplying out and stuff. So I have as cubed plus bs squared. I'm doing the inside first. The outside is going to be as plus b. And then the same sort of situation here, cs cubed plus ds squared plus cs 2cs plus 2d. So group up all the s cubes together and the squares together. Oops. And the s's. And the constants. So the constant is going to equal to 2. B plus 2d is equal to 2. And then there's another b and d together. And then everything else will equal to 0, right? So a plus c equal to 0, a plus 2c equal to 0. So we got a couple of paired up values here. So let's subtract. Let's solve for this first one. Subtract. So d is equal to 2. B is equal to, what happens when D is equal to 2? Is D equal to 2? Yeah. -6. One of those. So -2, 2, 4, 2, yep. So we got B and D, and I think this is just going to be 0 here. So if we subtract the top, we're going to get C equals 0 and A is equal to 0. So B and D are constants, A and C are 0, so that would make these all linear. So I subtracted, did what's that called? Algebra, yeah. Elimination. Sometimes it's called the addition method. Elimination method. Okay, here we have B is equal to -2, so all we have for the first term is -2. -2 over s squared plus 2. And then c is equal to 0, so we only have +2 over s squared plus 1. And then we also have this 10s. Okay. Questions? So maybe you guys should, over the weekend, try to review some partial fraction problems that you guys might have ran into back in Calc 2 days. Because there might be some shortcuts for some of these things that would make things a little bit easier to solve for. All right, so we're going to do the inverse Laplace transform now to get back to the real world. It looks like we're going to try to remember some of the transforms where we have a sine kt is equal to k over s squared plus k squared, and then the cosine kt is equal to s over s squared plus k squared. Right? So back in the real world over here, we're going to get our y t equal to, there's a -2 constant, but we're going to want a matching constant. So we might need just a little bit more work in the Laplace world here. So just a little bit more work to try to get this to match up to our formulas. We have an s squared plus 2, and if we write 2 as square root of 2 quantity squared in the bottom, then we know that the matching constant has to be square root of 2, right? But if we have a square root of 2 there, we want a -2 up on top. Does everybody agree that you're going to need a square root of 2 on the outside, negative? Okay. For the second one, our k is 1, so the 2 can just move on the outside. And then our last one, we already kind of have it set up. Our k is 1 also. Say it again. No, only the odd ones. So I was just looking at a Facebook post about your favorite theorem. Anyways, there's a theorem called the fundamental theorem of algebra, which says that your polynomial of any power will have that many roots, the same as your power in the complex world. Okay, so but your powers in complex world have to come in pairs and conjugates. So if you have a quadratic, it's possible that you have 2 conjugates and no real power roots. But if you have an odd number power, you could possibly have 2 conjugates, but you're guaranteed at least 1 real root. And I like Alan's description of the graphs of odd powers. They always cross the x-axis at some point. Whereas if you have even power polynomials, they come up, they go in the same direction where they came from, and so they're like parabolas or wiggly parabolas. So it's possible that some of those won't have any real roots. Anyways, back to our real world. We have our solution all set up now. We got square root of 2 or square root of -2, and then this was the sine function. sine root 2t. And then we have 2 times another sine function. This is sine of 1t. And then we have a 10 times cosine of 1t. So you see where the difficulty might happen, right? It's in the solving for y of s. I hope it's not too difficult. There is some room for error there, but a lot more room for error in the partial fractions. And once you've figured out the partial fractions, you also have to write your expressions now into something that you can change back into the t's. Okay? So you're going to be doing a lot of partial fractions, so you need to make sure that you, if there are any shortcuts or any tricks that you might have learned or you might have seen somewhere, I suggest we take advantage of that. Like I said, I'm not going to do any more partial fractions by hand. I'm just going to put it into the computer. All right, maybe we can get a glimpse of a third order. Because we won't have time to get into 7.3. I'm not going to finish it, so shoot, go ahead. Read it to me. Nice. All right. All right. So we need to remind ourselves of this transformation, and I don't know if you guys have it memorized already, but the s's decrease in power, and we start off with the y, capital Y, and then y, little y of 0, little y prime of 0, etc. And they all have negatives after that, by the way. Okay, so our transformation to the Laplace world is 2 times, we got s to the third power, y of s, and everything else is a minus. S squared go down in power and start the primes. The primes increase, so no prime. Minus s, and then now we have y prime, and then no more s and y double prime. So this 2 is all the way out here, so it's going to get distributed to every single one of them. Yeah, that whole thing is the third derivative. All right, so we saw this one. It says s squared y of s minus s times y of 0, little y, and minus s to the 0 power, and then y prime of 0. Minus 3, and then we have s y of 0, or y of s minus y prime of 0. No, that's just y. Yeah. Minus 2. Yeah, a lot of them, yeah. Except for the y double prime, which is here. So It's not that bad. So e to the t, remember what the transform of that is? 1 over s minus negative 1. What? S minus a, yeah. All right. So now, easy. Yeah. Well, let's knock a bunch of these out because of the 0. Right? We got a bunch of zeros there, and then 1, 1. So 2s cubed y minus 1 plus 3. Everything else is gone, so I can just drop the brackets. Minus 3s y s minus 2y of s equals that. And then, so if we imagine factoring out the y of s, which is what we're looking for, what are we going to have left? We're going to have a 2 2s cubed plus 3s squared minus 3s minus 2. And then we have a minus 2, which we'll bring over to the other side. So let's bring the 2 over to the other side, and let's divide out by this thing. So we got y of s equals, yeah. That's the first one, and then we have a minus 2 that became a plus 2 with this also denominator. Okay. So all you have to do is partial fraction this, which, I mean, yeah. Well, the thing is, you could probably factor this if you look at this. You could factor it. All right, this is where I take Mathematica out. So let's see. I have 1 divided by s plus 1 s. Doesn't matter. Doesn't matter. 2 s cubed plus 3s. Is it the exact same one? Yes, might be different. Bam. Just take it apart. So Mathematica combined it and solved for it and put it together. And so now we have 1 over s, 1 over, so we got an e to the negative s, e to the s, or e to the t, e to the negative t, e to the negative 2t, and e to the 1/2 2t. Mm. No mathematics. All right. So once you have this, it should be easy to go back to the real world, right? Again, you have to do this partial fraction business. So Wolfram alpha, the keyword is apart. See, you can say apart, and then in brackets, you can write down whatever it is you're trying to take apart. All right, so we have homework due. Oh, so I was talking to Adam about this. The homework that was supposed to be due this Sunday, I actually made it due next Sunday. Is that okay? So the homework that's supposed to be due next Sunday would be up to 7.2, but I think I'm gonna, yeah, it'll just be a 7.2 because next week we'll do 7.3. I'm not planning to change the dates for the homework that's due on 11 in November. Yes, get ahead. All right, have a good. Well, I'll see you guys next week. Have a good weekend.